Okay, so my talk would be based on the topic of number fluctuation from molecular dynamics. I'm Volodymyr Kuznietsov, a graduate student of Vladimir Vovchenko in the University of Houston and former student of Mark Gorenstein in Kyiv National University. So we would base our talk on such plan, started from the introduction, then go into the details of the simulation, talk about the pure phase in our simulation and mixed phase in our simulation, and then close our talk with summary and discussion. To make it short, the topic that we're trying to study as a previous author is QCD matter. So naturally, we're interested in the question of the features of the critical point in such matter. And we're trying to consider some kind of quantities that can be observed, namely scaled variance or normalized fluctuations. So here you can see the basic idea, not connected to our precise study, but the idea that in the onset of critical point, we would have a dramatical increasing of fluctuations. You can see here the example for van der Waals, a simple classical model, and also how it can be looked on the phase diagram with fluctuations. So, namely, in our case, we will study some approach that connected to the experiment, because in a theory, we would have coordinate or momentum space, and in experiment, for example, some kind of Harian's collisions that can be performed in reality, we have only momentum space. Also, another important feature is that in theory we have contact with the heat bus, with what we usually not have, of course, in Harian collisions. Also, we have conserved charge and uniform media, also fixed volume. All these features cannot be usually introduced in the experiments because we have, of course, non-conserved particle numbers, inhomogeneous system, and fluctuating volume. So another reason why it's interesting to study some kind of phenomenological approach is to connect experiment and theory. And of course, in both situations, we need microscopic description of fluctuation, with what our model can be very helpful. So we consider one of the simplest from the attractive and repulsive potentials, Lennard-Jones potential. In our case, we studied only the onset of fluctuations above and onset of the critical point above and below the spinodal region. So we're not interested in all this hard phase diagram, but nevertheless, it's good to know about it. And you can see here on this picture how looks the potential and how the phase diagram of all phases looks in Lennard-Jones fluid, which is of course not very real because the potential is classical. It's both not relativistic and not quantum one. So some details of our simulation. We consider just classical Newton system of equation and solve them to simulate the movements of particles with such potential. We also use classical definition of time averaging for understanding the all mean values of our observables. Of course, it's a bit tricky because, for example, we need to have temperature that is corresponds to the point that we study on phase diagram. We need to have density and stuff like this. But it's a bit short of time to get into it very precisely. You always can check our works on Archive or VRS to be very into it, or ask me after the talk. So another important thing here is that we cannot study fluctuation in all our volume, naturally, because our volume is 400 particles or something, it's conserved, so particle number fluctuations are not, it's not fluctuating in our volume. That's why we need to cut some sub-volume and study fluctuations in it. And you can see here first approach to it. This increase in fluctuation is not very real. Why? Because this is our estimation. Like if we have large system, for example, 400, 1000 particles, 5000 particles, and in all the situation, we should observe something if we expect to be in a grand canonical ensemble. Of course, it's like a rude estimation, but in this case, we would use this formula naturally to obtain variance. And we use this just to check what can we obtain from our pressure computed in the simulation. You can see here that this increase is very high, and we also checked it with the virial expansion for Leonard-Jones. You can see they're quite consistent. And again, even virial expansion show you some increase in the fluctuation. The main result of the first part of our work is these pictures. So these fluctuations are computed in a sense of just definition of fluctuations as dispersion of our number distributions, probability distributions. So these fluctuations are consistent with the fact that we have our small system, and also we use here techniques to understand the corrections to the size of our system. So you can see that in the small densities, we have small fluctuations, and when density increases till the critical point density, 0.3, you obtain larger and larger fluctuations. What in our situation can be considered as a feature of nearby to critical point? Of course, when we get further to the larger densities, fluctuations get smaller and smaller. Another thing that's interesting to see here is that when we increase in number of particles, our fluctuations get bigger and bigger, but of course still smaller than this red line. This red line represents our estimation that I showed before for the grand canonical ensemble. So namely this slide. And this estimation shows that even for 25,000 particles, we are still far away from grand canonical ensemble. So unfortunately, this estimation is not true. So our system can be considered as close to infinite system. Another important result is that we can perform momentum cuts in our system, and this gives some opportunity to obtain fluctuations in a case of momentum space, which actually closer to real fluctuations that can be observed in heavy ion collisions. But unfortunately, as you can see on the panel below, in this case, when we perform momentum cuts, we cannot observe any features of critical point. So our fluctuations, scaled variance, is always below 1, which corresponds to it's close to the ideal gas case, the red line here. After that, we considered the mixed phase region. Here you can see the small part near to the critical point of the phase diagram, and the upper line corresponds to the first part of the work. So here we study pure phase. Second one corresponds to the second part of the work, so lower one, where we perform a study of the mixed phase. So nucleation region, the region of spindle decomposition, and cavitation region. They are colored differently, and it would be important in next slides. Here you can see just a simple representation of our understanding of the 4 regions. So gaseous phase is just pure phase, when you have free particles and you cannot have any serious clusterization of something, nucleation region where you have clusters, so it's like small bulbs of the new phase in the old phase. After that, it's spinodal decomposition when we have separation of phase inside of mixed phase, and cavitation where most part of fluid is already high density fluid can be considered as liquid, and some bulbs of gas in it. So first model that we use to understand our fluctuations in this case is Fisher-like cluster model. So we choose the simplest one that we can derive explicitly and obtain fluctuation in it. Second model that we use is so-called Minecraft model proposed by one of my colleagues. We use some understanding of geometrical features of our system. Consider a bulb, square-like bulb. It sounds strange, but again, just a model understanding of liquid that intruded a square-like bulb that we actually observe. So you can see it on the picture, B and A. This model gives us an opportunity to separate effects of geometrical inhomogeneity of our system. And as you can see on this picture, here, this model is quite close to our results. So here, solid black line corresponds to the simulation. So it's just statistically obtained fluctuations. And there you can see here, very large, corresponding to the first part of the work. But as we see from two our models, namely cluster model, the orange line, and dashed black line for the Minecraft model, you see that this fluctuation that we obtain in our simulation is not really a feature of the critical point. Mostly, they are connected to the geometrical inhomogeneity of our system in this case. So to sum it up, molecular dynamics simulation with Leonard-Jones fluid provide a microscopic approach to study critical point fluctuations. Scale variance of particle number is computed along the supercritical isotherm and subcritical isotherm, as it's shown on our pictures, of course. Large fluctuations are observed near the critical point when calculated in coordinate space, but washed out when momentum cuts are imposed instead. And large fluctuations are found in mixed phase, but phenomenological study shows that they have mostly geometrical nature, not due to the closeness to the critical point. And about our future plans that I'm trying to perform now, fluctuations in expanded systems seems interesting to study, especially with collective flow, because when we use ensemble averaging, it's much closer to the real case of heavy-ion collisions than our simulations that we showed before. Because, of course, you're not having a heat bath, you don't have anything like uniform media, and we cannot study it like this in experiments. They cannot compare our results with the experiment one. The next idea is simulation of higher cumulants, both in pure and mixed phase. And this study is a bit tricky, but nevertheless, it's interesting to try it and check results we can obtain. Of course, for higher cumulants, we need higher statistics, so it requires more technical advantages. Also, precise study of the subvolume, form effects, and finite size effects in the mixed phase. Is it possible to reach the thermodynamic limit? Is philosophical question in this case, because our study now shows that we cannot obtain like some kind of model to get lower bound of this limit at least, but maybe it would be possible in the future. Our model, our simulations give us no idea about mixed phase in this sense. Also search for similar effects in the quantum and relativistic model, because maybe these effects would vanish due to quantum or relativistic nature of strongly interacting matter, but nobody knows again. So thank you for attention, and I'm ready for questions.
Okay, thank you for your talk. Please, questions.
Sorry, what order of high cumulants you will investigate in future?
At least skewness and kurtosis. The study of this cumulants was performed in the previous articles of my colleagues, so I would be interested to compare like mean field model, for example, results and our results here.
Okay, thank you very much. Thank you.
Thank you, Volodymyr, for a very interesting presentation. And this is the results that we already hear from Mark Isakovich in our institute. But I would like to ask you about fluctuations and molecular dynamics simulations that you had. The most important, as I understand, this is the repulsion in the potential, Lennard-Jones potential. So if you omit, for instance, attraction part, you still will have the same result, probably, or not?
I don't think so. So
my question is related to these two parts. So if you, it is clear, if you don't have repulsion, everything stack to one cluster. But if you do not have attraction, so what is the role of repulsion and attraction in this case?
I mean, in our case, if we would be deeply into the simulation that we have, I think that both parts are important of the potential. Why? Because if you look at the equation 5, for example, yes, you would obtain a strange result if you have only repulsion, yes? This result would be strange in a sense that consider a periodic box setup, yes, and all these particles would be just shoved one from each other, yes?
Yeah. There is very short answer, but you explain very complicated way. If you have formula for fluctuations in van der Waals model, then it is very clear that if you have only repulsion, your fluctuation is smaller than in the ideal gas. If you have attraction, then it could be larger. Without attraction, you never obtain large fluctuations like critical point, phase transition, and so on. So all these phenomena due to attractive forces. Repulsive forces only suppress fluctuations. This is,
I want to say that our simulation probably with only repulsive potential would be also not very physical, because we consider closed system, yes? So
but, of course it is possible because you consider your particles in the box, so with the periodic boundary conditions. So if you have only repulsive forces, they still in the box because of the boundary conditions. So it will be no problem, but fluctuations will be smaller than in ideal gas. It means this scaled variance is smaller than 1. For ideal gas, it is exactly 1. For repulsive interaction, it is smaller than 1. If you have attractive, it can be larger, and very large also would be. Yeah. Okay, please, other questions? Okay, yes, please. If not, then we thank you again for very interesting talk, and I give the word for scientific secretary.